Okay. Can see the document? Anybody?
Yes.
Okay, thanks. Okay, so let's continue with the nuclear physics, the one we did yesterday. So I think I introduced you with the E equals mc squared. So we went in depth about what is meant by the mass. Mass is called mass defect. What is meant by mass defect? Loss in mass when nucleus is formed for all its constituent nucleon. The difference between the total nucleon minus the mass of the nucleus is called mass defect. So this mass change, we found that only happens during nuclear reaction. Normally, energy change equivalent to the mass change, E equals to mc squared. And we work out what is meant by 1U, unified atomic mass. So 112 of the mass carbon 12 atom. And the energy of 1U equivalent to 933 mega eV normally. Okay, so today we're going to talk about binding energy. Okay, let's go to the PowerPoint. Okay, so binding energy. Okay, what is meant by binding energy? So the fourth point is the definition of binding energy. Okay, binding energy is defined as the energy required. Okay, there is a two important word missing. You need to add the minimum. Please add the minimum energy required to completely separate the nucleons of a nucleus to infinity. Please add these two words. So what is binding energy? The minimum energy required to completely separate all the nucleons of a nucleus to infinity. Okay, that's called binding energy. You can see this diagram here on top. The helium, the proton, neutron already are bonded, but what is the energy you need to supply? How much of energy you need to give so that you can split all the nucleons from the nucleus to infinity? That's called binding energy. Okay. So within the nucleus, there are strong forces. You know what forces is that? The strong nuclear force, right? The strong nuclear force, which bind the proton and neutron together. To completely separate all these nucleons required energy. Energy referred to binding energy.
Okay. I found this on my book. It says another definition, which is this correct? Binding energy of a nucleus is the energy needed by the nucleons in order for them to do work to assemble the nucleus.
The other way also can.
Okay.
The amount of energy required to split them, or another definition, the amount of energy released when the nucleus is formed from the nucleons. Both can. But I stick with this. The amount of energy required to separate them to infinity.
Okay.
Okay. So yeah. So it is the energy. This binding energy is equivalent to the energy of mass defect. The energy of the mass defect. So earlier you see this calculation you found what is the energy equivalent to the mass defect. You count for carbon is 102 mega eV, and this is the binding energy of carbon. Okay, the binding energy of the carbon is 102 mega eV. The amount of energy required for them to form or to split them. So the binding energy is equivalent to energy equivalent to their mass defect. Okay. Okay, so when separated nucleon combine to form a nucleus, there is a reduction in mass, equivalent amount of binding energy is released. Yeah. When form also the energy is released. Okay. When split, remember when split them, you need to supply energy. When the nucleus is formed, energy will be released. With one condition, the nucleus formed is a stable one. Okay, stable one. Now tell me. Go to one example. Okay, sorry. Okay. You have uranium. You have carbon. Carbon 12. Uranium nuclear number is 235. Carbon 12. It's a carbon 12. Carbon 12 atom. Tell me, carbon or uranium will have a greater binding energy?
Uranium.
Yes, good. Uranium will have a greater binding energy. Okay. Why?
More strong nuclear force exists.
Instead of more strong nuclear force, I think the number of nucleons is small.
Oh, okay.
Because the amount of nucleus you need to separate them to infinite is 235. Carbon only 12.
Okay.
So I think uranium will possess lots of binding energy. Okay. Carbon will have a less binding energy because the number of nucleons is limited. But is that means greater binding energy means the nucleus is more stable?
No.
No. Not necessarily greater binding energy means the nucleus is more stable. So, because we know carbon is more stable than uranium, carbon 12 is stable than uranium. So, what determines the stability of the nucleus? Something linked to binding energy, but we call it binding energy per nucleon. Okay, how much of binding energy possessed by each nucleon? That determines the stability of the nucleus. So how do you find binding energy per nucleon? So binding energy of the nucleus divided by the number of nucleon it has. You get the amount of joule per nucleon. Binding energy nucleon measures the stability of the nucleus. Okay, so greater the binding energy per nucleon means more stable the nucleus. Not referring to binding energy. Binding energy per nucleon must be greater for stability. But I don't know why in Cambridge, most of the time, the one has a greater binding energy looks like has a greater binding energy per nucleon. The way the question has been asked, greater binding energy per nucleon means they have a greater binding energy. The type of question asked in Cambridge. Okay. So one example, helium nucleus, helium-42, the mass of proton, neutron, helium is given. Find the mass defect, find the binding energy, find the binding energy per nucleon. Come on, give it a try. Just warm up. U will be what? U is 1.66 times 10 power of negative 27 kilogram. So how do you find mass defect? Mass defect, of course, right? 2 proton plus the 2 neutron minus the mass of the helium nucleus. Minus with this. look at in terms of what? In terms of U. They now define binding energy. mc squared. M must put it in terms of kilogram. U change to kilogram times with 1.66 times 10⁻27 times with speed of light squared. You get the binding energy. And that binding energy divided by what? You get a binding energy per nucleon. Then binding energy divided by the number of nucleon you have. So helium possess 4 helium, 4 nucleons, so divide by 4. So yeah, so this is hope this is in your mind. So 2 proton, 2 neutron minus this is the total nuclear mass. Helium mass is this. The differences give you the mass defect. So mc squared gives you the energy, and divide by 1.6 10 to the negative 19 given EV 28.4 mega eV. So 28.4 divided by 4, you get binding energy per nucleon. I think in a nuclear process, energy normally will be stated in terms of mega eV or EV. If they never stated what the unit they want, you can leave it as joule. Okay, let's work. Any question from this slide? Okay. Okay, we hold on to this question first. Hold on. We go to this stability first. Okay, so scientists done finding they did find the binding energy per nucleon for all the elements in the periodic table. They found the graph like this. Y-axis is binding energy per nucleon. The x-axis is the mass number. Of course, another name is nuclear number. Nuclear number. So proton plus neutron. So the found is like going the binding energy per nucleon increases, then it started to decrease. So they found that the most stable element, I mean nucleus in the world, is found to be iron. Okay, iron is the most stable nucleus. Means what? It has the greatest binding energy per nucleon. Okay, iron man. So maybe in chemistry you found iron is not stable, but in chemistry we learn about iron in terms of stability of the electron, right? How fast it can get lost. Okay, what that stability and this stability difference?
And this is the nucleus.
Now this is about the stability of the nucleus, the headquarter. Chemistry never really you never really go in depth that if you bought element today, let's say maybe aluminium, you thought in billion years later it's going to be still aluminium. Chemistry say it might be rusted, but according to physics, even the nucleus will be changed in coming time. Aluminium may be converted to another element because the nucleus itself has some certain stability. Okay, so that's what reality. Okay, so all the elements, other elements like uranium, you see uranium is far to the right. They are not stable, but their mission is what? To change to a stable element. Okay, by doing what? What process?
Fission.
Fission. So uranium can reach more stable element by reducing the size of the nucleus by doing fission. So few chain of fission process can increase its stability until it reaches the most stable element, iron. This required a very long period of time. Uranium not directly going to change to iron. It changed to another element. Many intermediate elements will appear. About maybe 15 intermediate elements roughly. Okay. Yeah. So the one with a greater nuclear number than iron will experience fission. The one smaller nuclear number than iron. So for this case, you have to remember the nuclear number of iron by heart. Nuclear number of iron is 56. More than 56 nuclear number element will go fission. Less than 56 nuclear number element will experience fusion. Likely to experience fusion if the environment permitted. If it permits the correct temperature, correct pressure, fusion can be initiated. So yeah. But anyway, all elements want to convert to stability. The most stable ideal nucleus they want to have is iron. Okay. But tell you the truth, the uranium will convert. By the time reached iron, I don't think so. Is it our universe going to exist or not? Because it's going to more than billion years to reach iron. Okay. Even they said uranium going to stop at the intermediate stage, at lead, Pb. Lead is quite a stable element, but not as stable as iron. But lead to convert to iron, they said the half-life of lead is quite huge. Like maybe comparable to the age of our universe, around 13.7 billion years. Okay, so we can't see lead converting to iron. I don't think so. We can able to see that because, as I said, you know, is it our universe going to be there or not? Our sun is expanding, so lots of uncertainty. So majority of element, I think most likely will reach lead. Okay. Do you understand? Any questions? Sorry. Any questions? So this is about stability of nucleus. Stability of nucleus determined by binding energy per nucleus. Okay. Okay. Now this is another graph, not that important. Just skip this. Okay, so let's go a little depth about fusion. Fission, you know this before. Fusion, what is that? Nuclear low mass number may undergo nuclear fusion. In general, nuclear fusion possible. Final product has a more binding energy per nucleon. Of course, all the natural occurring nuclear process, which binding energy is greater? Which binding energy per nucleon greater? The reactant or the product?
Reactant.
The product.
No, product.
Okay. Greater the binding energy per nucleon means more stable, right?
Yes.
Okay. Yeah, more stable. But as I said, Cambridge always going to say that more greater binding energy per nucleon means more binding energy, like that. Okay. So reactant or product has more binding energy. We say product has more binding energy. Okay, product has more binding energy. Therefore, there will be a net energy release. There will be a net energy release. Okay. So this is fusion. Hydrogen merge form helium. Fusion process happens in the sun. But this process to happen, you need a very high temperature, 1,000,000 degrees Celsius. Okay. So the energy generated in the sun is due to this process because energy release in the fusion process is very much greater than energy release in the fission process. I already told you why. Why energy in the fusion process is very much greater than the fission? Why? Because the number of nucleuses per unit mass of fusion element is greater than the fission. Fission normally uranium, very big size. Fusion is hydrogen. 1 kilogram of uranium, 1 kilogram of hydrogen. I think 1 kilogram of hydrogen has more nucleus because one hydrogen nucleus is the mass is too small. So you have more fusion reaction. So more energy will be released per unit mass of the fuel. So the example of nuclear fusion, yes, this is one example. Energy release. Exothermic process. Okay. The next is fission. Fission is, of course, process of heavier nucleus tend to disintegrate into lighter, more stable nucleus. Okay. The fission fragments have a greater binding energy per nucleon. As usual, the product will have a greater binding energy. Okay, especially binding energy per nucleon. More stable. So neutron was bombarded to uranium. Uranium 235 become 236. 236 become a very unstable stage where most probably can fissile easily to become fission to happen. So fission happens. So create energy. Okay. Okay, so that's about fission. Fission, naturally occurring process, always release energy. It's an exothermic. Okay. When a nuclear reaction release energy means the product or reactant has more binding energy. The product will have more binding energy. Okay, especially binding energy per nucleon. Okay, let's try one question. Yeah. Okay, this is one question. Now we're going to calculate how much is energy release for this process above. It's a fission. Okay, when you look at it, you know it's a fission process. Uranium, heavy nucleus bombarded with neutron, produces daughter nucleuses and some radiations. Okay, here they give binding energy per nucleon for each product. They give binding energy per nucleon for uranium. La and Br is given. Okay. This all are binding energy per nucleon. Okay. Identify X and Y and complete the equation. What X and Y represents in this equation? So balance the numbers. What do you get for X and Y? I think X you get 1, 0. Neutron. And Y is the gamma. If you check 236 minus the 146 minus 87, I think you get 3. So 1, 0, 1, 0, 3, 1, 0. So it's neutron released. You also should know that it's a fission process. Right? So one neutron going to form another 3 neutron, right? Chain reaction. And another one is a 0, 0 value. So it should be a gamma ray. Gamma ray is released. So X is neutron, Y is gamma ray. Okay, A2, name this type of nuclear reaction. What is the name of this nuclear reaction? Fission. It's a fission process. So how to know it's a fission? The real exam, let's say they never give uranium, La, Br, they just put the X become Y, Z. How do you know it's a fission process? Check the size of the nucleus. Check the size of the nucleus. The size of the nucleus of the reactant big than the size of the nucleus of the product. So it's a fission, size getting smaller. Okay, fission. Okay, next, explain why neutrons are used to split uranium. Why not proton? Why not electron? Why neutron?
Have no charge.
Have no charge, yes.
Won't be
have no charge, so easily can get into the nucleus, okay, without any repelling force. So yes, neutron is used. Okay, now the most important, the purpose we are doing this question is the last two. Sorry, especially the B. Estimate the energy amount of energy release. For this process, how much energy is released? How are you going to calculate that? You know, energy release is E equals to mc squared. So if you want to use E equals to mc squared to calculate energy, you need to find the mass defect. The mass defect is what? Mass of the reactant minus the mass of the product, right? The total mass of the reactant minus the source mass of the product, you get mass defect times with square speed of light, you get that energy release. But the mass of the reactant here is, who's the mass of the reactant? Mass of the reactant is 236 uranium after merge. This is your mass of the reactant. Mass of the product is the entire product comes out without including gamma. Gamma don't have mass. The La, Br, and the neutron together is going to be the mass of the product. So you minus, you get energy. And their mass must be given 5 to 6 decimal places, then only you can see the mass defect. But this question, they never give the masses of individual particles. They give binding energy per nucleon. Okay. Sorry. So if they give binding energy per nucleon, you have to use another way to find the energy release. What way? You must use the binding energy concept. Which binding energy greater? Reactant greater or product greater? Guys, which binding energy greater? Reactant greater or product greater?
Product.
Product greater. Product has a greater binding energy. So what do you do? The energy release is this is another new formula. What do you call? Alternative to MC square. The energy release is the total energy, binding energy. This total binding energy of product minus the total binding energy of reactant. This is also another way of finding energy release. Total binding energy of product minus total binding energy of reactant is the energy release. Alternative to MC square. MC squared you can't use here because they didn't give the mass for each element. Okay, so now how do you find binding energy of the product? Who are product here? La, Br, neutron, gamma. Gamma don't have is EM radiation. So La, Br binding energy per nucleon is given. So La is binding energy per nucleon. How do you find binding energy of La? Just 8.41 times with the nucleon number. 146 times 8.41, you get the binding energy of La. Then do the same thing for bromine. 8.59 times 87, you get the binding energy of bromine.
The neutron doesn't have.
Yeah.
The neutron doesn't have one, right? Because it's not in the nucleus.
Okay. That's another question they ask. Why neutron don't have binding energy? Why neutron don't have binding energy? Because it's a single particle. It doesn't bind with anything.
It's not touching.
So the answer is neutron is a one isolated particle, one single isolated particle. So it does not bind with anything. So therefore it doesn't have binding energy. Okay. So next time they'll ask why neutron don't have binding energy. So you say it's a singular or individual particle, does not bind with any other particle, therefore it doesn't possess binding energy. So what is the total binding energy of the product? Just La plus the Br. Okay. What is the binding energy of the reactant? Just the uranium, 236. So you minus these two binding energy, you get the energy released. Remember, the neutron was not included in calculating the energy released by using a binding energy method. But the mass of the neutron is considered if you find energy released by using MC squared. MC squared, all mass are considered. Binding energy method, the individual particles exist alone. They don't have binding energy, so they won't involve in the binding and in the energy release calculation. But both methods will give the same answer. Remember, two ways of finding the energy release. If MC squared means to find the mass defect, the mass of neutron needs to be considered. the total mass of the reactant minus the mass of total mass of the product. Total mass of the product must be La plus Br plus neutron, 3 neutron. Remember. Any questions? No questions. Hope you understand. So now go for the working. So we're done with the A, part B. Binding energy of La 1468.41 Br calculated. Binding energy of the product is the La plus Br added, so 1975.19. The binding energy of uranium was calculated, minus you get the energy release. So 184 mega EV was released for this process. Okay. The next. Suggest how energy is released during this nuclear reaction. Okay. How this 184 energy is released? Of course, in terms of kinetic energy of the product. This 184 will become the kinetic energy of the La, Br, neutron, and gamma. Kinetic energy of the product. But eventually, later, it will turn to become heat. Finally, it changed to heat. Kinetic energy later changed to heat. Okay, and the heat is the one used to vaporize the water to become steam, and steam allowed to run the turbine, and you got electricity. So what happened to the energy release? The energy release will be in form of kinetic energy of the product, which eventually changed to heat. Okay. Any questions? So what you learned something new here? You learn how to find energy release by using binding energy value. They'll give you binding energy per nucleon times the nucleon number, you get the binding energy release. Another one difference, be careful. When you use E equals to mc squared, the mass defect you calculated, mass of reactant minus mass of product, or mass of product minus mass of reactant. Mass defect. Mass of reactant minus mass of the product. Because mass of reactant normally higher. Mass of reactant will be higher than mass of the product for naturally occurring nuclear process. For binding energy, how do you find the binding energy? The binding energy of product minus the binding energy of the reactant, you will find the energy release. Can you see the difference? Mass defect, reactant minus product. Energy release through binding energy product minus reactant. Okay. So when a nuclear reaction happens, naturally occurring nuclear reaction, product will have a very little mass, but product will have a greater binding energy. Remember. Or in other words, greater binding energy per nucleon. If naturally occurring process, which normally exothermic. Okay. Human-made nuclear process, all we want exothermic or endothermic. The nuclear process we are doing in the nuclear reactor, we want the process to be exothermic or endothermic? Exothermic, right? Because we want energy. We want energy to run the turbine to get electricity. But even though I told you, did I tell you that some nuclear process, man-made nuclear process, is endothermic? Okay, let me go to this. Okay, so let's say X become Y plus Z. One nuclear reaction, one nuclear process. Okay, nuclear process. Exo means when exothermic, we know is YZ more stable. More stable. YZ as a lower mass. Y plus Z as a greater binding energy. Binding energy. This is what conclusion we make. But sometimes endo. Okay, endo happens when let's say A become B plus C and it's found to be endothermic. If endothermic, you mean what you can tell about product? Product will have a greater mass or smaller mass than A. All going to be the other way around, right? The B and C going to have a greater mass than A. Mass has been gained. Energy has been absorbed. Endothermy. The binding energy of B and C increased or decreased? Binding energy per nucleon decreased. The binding energy per nucleon will be decreased. Okay, that means B and C more stable or less stable than A. If a nuclear process endothermic, then B and C going to be less stable. It's less stable than A. Is it good for us? Yeah, sometimes it's good. You see, some medical term. I told you this, right? Did I told you this about this? Why we need to have endothermic sometimes? Anybody? Did I told you about endothermic nuclear process?
To store?
I told you.
Wait, I don't think so.
Okay, some nuclear process we do purposely we have endothermic because we want to create a nucleus, an element, a product, element which is less stable. Less stable. I don't know. I forgot the name. Start with T. I forgot the name of that element which used to produce by using a nuclear process, but the element produced is less stable. And that element as a half-life, I think few hours. I think 6 hours, if I'm not mistaken, few hours. And this element will be injected into your body. The person who have maybe suspected to have cancer cells in their body, so they inject this element into the body. Then what happens? This element has a tendency to go and find wherever there is a nuclear or wherever there is a cancer cells. This element will has a tendency to go around that nucleus, surrounding that nucleus, the particular nucleus which is a cancer cells, and 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 stays there for a while. Because it's a radioactive substance, it emits gamma ray. It emits gamma radiation. For how long? For about 6 hours. So the person who was injected with this element, what happened? When he stands there, okay, gamma radiation is coming out from his body. Okay, not a very strong one, small gamma radiation. Because the amount injected is controlled. So the gamma radiation only will come out with where the cancer cells are located. So what in medical they do, they take a picture called gamma photography, if I'm mistaken. They get the image where the gamma radiations are coming out from the body. Wherever the gamma radiation coming out, let's say gamma radiation coming out from the head, they knew that the cancer cells, there is some cancer cells in the head, and so on. So used for medical field to identify cancer cells, they use this nuclear process, which is endothermic. They create an element which is more unstable. Okay. So in your examination, don't think all nuclear process are exo. It could be endo also. How to check? Is it endo? Check, is it mass rising? If the mass of product greater than the mass of reactant, it's endo. If the product less stable than the A, endo. It's an endo process. Any questions? Hope you understand.
Teacher, the binding energy, do we need to calculate it or is it provided in the question?
Which one? The kinetic energy.
The binding energy.
The binding energy, if they want what is the energy release, they'll give binding energy per nucleon. They'll give, you want the individual binding energy. The individual binding energy will be given, but they'll give in form of binding energy per nucleon normally.
So we cannot calculate the binding energy straight from the defect in mass?
Let's say let's say you want to know binding energy for B, binding energy of B. Okay, they give information about A and C. They're asking to find binding energy per nucleon B. Maybe the B is above nucleon numbers 80, down is 20. You want to use only what, the nucleon mass minus the mass of the nucleus. You are saying this method, right?
Yes.
To use this method, we must give the mass of the proton, mass of the neutron in 6 decimal place. If they never give this, you cannot use this method. Correct? So this method only can be applicable if the proton neutron mass is given in 6 decimal places. If this value not given, that means they are not, you can't use this method lah, because you don't lack of information. So you have to go this method. The binding energy of the product minus the total binding energy of the reactor will get the energy release. Okay, Shike?
Okay.
Yeah. So depend to the availability of the information. Availability of information. Okay, so any other questions, guys? So remember, the nuclear process, don't take it always exo, can be endo. How to check? You have to check, is it mass increasing or not? The calculation part A, part B will already tell you, reveal that. Its mass is increasing, then the next question they will ask, is it endo or exo? So you have to say it's an endothermic because mass has been increased. That means energy has been absorbed from the surrounding to create the mass. Okay. Mass drop means mass change to energy. Mass increase means energy change to mass. That means from where they got the energy? From the surrounding law. So you need to apply that energy. Okay. Okay, so that's the answer for this. Okay, this is another question. I skip this first. I just go to the, okay. Yeah, that's the first part of the topic. Let me go to one pass here. Just one pass here question. Oh, no questions like that. Okay. Okay, we can use these two. November 7, one example. So explain what is meant by binding energy of a nucleus. The minimum energy required to separate all the nucleons of the nucleus to infinity. Okay, so it's called binding energy. So binding energy versus mass number is shown. It's a binding energy per nucleon. We know this graph. Okay, top is iron. Okay, so this is the reaction. Okay, on particular fission reaction, this happens. Label the approximate position of uranium, barium, krypton. So you have to be careful here. Do you need to plot it to the right of the peak or the left of the peak? So you need to remember the iron for this law. Iron is what? Nuclear number 56. So all three of them are more than 56. All these three particles are located on the right hand side. Of course, uranium first law on the right hand side and the other two. Don't go to the left. Okay. That's how you located this. The neutron that is absorbed by the uranium nucleus has a very little kinetic energy. Explain why this fission reaction is energetically possible. Okay, why this nuclear reaction? What's the answer? Why this nuclear reaction is energetically possible? Because energetically possible means why this reaction can happen naturally. Naturally means you don't need to supply any energy. Okay, because it's an exothermic process, right? So what do you say? Anybody? What's the answer for this? The neutron that is absorbed by the uranium nucleus has a very little kinetic energy. You know, just now I told you, in this diagram, A become B plus C. It's an endothermic process. Okay, let's say the energy absorbed is 10 EV, 10 mega EV. The energy absorbed, let's say 10 mega EV. How do you supply this energy? The energy is supplied in terms of kinetic energy of the reactant. Maybe let me modify this equation. Let's say A plus B become C plus D. It's an endothermic. Okay, it's an endothermic process. So 10 mega EV need to supply. How do you supply this energy? By giving kinetic energy to these particles. Initially they must have some kinetic energy, which this kinetic energy must be at least equal to 10 mega eV. Then only this process will happen. Okay, because you need to supply energy. The energy will be supplied in terms of kinetic energy of the reactant. Okay, so this question, they said the uranium was collided with what? With the neutron, which has a very little kinetic energy. That means there is no initial kinetic energy. Then they said why this process can happen energetically possible. So you said, what are you going to say? Because you said the uranium based on this graph law. So you said what? The product is as a greater binding energy per nucleon than the reactant. Okay. Therefore, it's an exothermic process. It's an exothermic process. Therefore, the reaction energetically possible. Okay, from less stable to more stable is always energetically possible. Because of what? There will be a net energy released. So that's what you have to say. And that's the answer for this. Okay, so why is energetically possible? You said the product has a greater binding energy per nucleon than the reactant. Therefore, the conversion happens from stable to unstable. So the process is an exothermic process. So energetically possible. Okay, any questions, guys? So this is how the question is going to be, finding the binding energy. Okay, so time's up. So what you learned today? So you learn about how to calculate the binding energy. So you introduce with the binding energy and how we calculate 2 ways, mc squared, binding energy per nucleon, product minus reactant, you get the energy release. And we talk about the graph, binding energy per nucleon, the most stable element is iron. Any questions? Yeah.
I have a question out of syllabus.
Yep.
If you say iron is the most stable element, then the sun undergo nuclear fusion. Then won't it just stop at iron and not go further?
Okay, very good question. Okay, so you said, yeah.
That's only for larger suns, right? Like larger stars.
Yeah, correct, good. Our sun is a big sun or a small star. It's actually an intermediate star, not a very big one. Our sun is an intermediate star. So the center core hydrogen has enough pressure from outside, because our sun is an intermediate star, not a very big one. The pressure is quite good, so that the hydrogen convert to helium. But when the core become helium, the size of our sun is not that big. So the pressure required for the helium and helium to merge, okay, not enough. Because to merge them, you need to have the helium need to have a greater kinetic energy. Because helium has a two proton inside now. So the electrostatic force is much more stronger than hydrogen and hydrogen. So to have a greater kinetic energy of helium, you need a more immense temperature, very high temperature. Hydrogen to merge, you get million degrees Celsius. Helium to helium merge, I think you need maybe 100 million degrees Celsius. So to get 100 million degrees Celsius, you need to have an immense pressure from outside. The pressure depend to the size of the sun. More bigger the size, more weight outside, more gravity. So the pressure going to be very large. Yeah, helium can convert to hydrogen. But our sun can't afford to change helium to hydrogen. So our sun going to stop at helium already. But if you go for a star with 50 times bigger than our sun, the core will change to hydrogen, change to helium, change to other metals until it can reach to iron. Okay, reach to iron. I think you know black hole.
Yes.
Black hole. Who become black hole? Very big star, you know. I think star more than 80 times bigger than ours. As black hole, the core become hydrogen transferred to iron, then iron will be destroyed to become neutron. Okay.
Or that becomes neutron star. Okay. It becomes neutron star or black hole depending on.
Yeah. So become neutron star. If more pressure, even neutron will turn to become a singularity, become a black hole. Because iron is made of what? Center nucleus surrounded by electron, right? The pressure is very high. What happened? The electron, the orbiting electron also can't stay there, you know, for a big stars. The electron will collapse to the nucleus. The electron orbiting collapse to the nucleus. The proton inside the nucleus and the electron will merge, form neutron. So you don't have iron anymore also. So no such thing as atom line that planet. It's called neutron star. Neutron star will form. Neutron star is the like a secondary to black hole. Black hole is the even bigger one. Even neutron star is all combined form a singularity, become black hole. Yeah. So Gavin, do you understand?
Yes, thank you, sir.
This is cosmology. Cosmology, not in your syllabus, but this topic has been included for next year. Next year is a new topic included in Cambridge syllabus. You didn't read this. Next year, cosmology will be there in A2. Okay, so thanks. So I see you back tomorrow. Thanks. See you. Bye.